Okay, here we are now into the second section of Chapter 8, so I'm guessing you have a pretty firm foundation of the basics of solution formation and the properties of solutions and types of solutions that are possible. So let's move further into the chapter here in Section 2. Okay, and as you can see here, this section is going to be on electrolytes and non-electrolytes. So we're going to define those terms, and I think you'll probably take to them pretty quickly. I'm sure you've heard the terms. A lot of those sports drinks sell you on the electrolytes that they contain, but again, electrolytes are not terribly exotic. It's just a fancy word for something that many solutions indeed have. Okay, so in water, we have strong electrolytes, which separate into ions, making solutions that can conduct electricity strongly. Weak electrolytes separate just a little bit, so they only produce a few ions that will only conduct electricity weakly. And then finally, non-electrolytes produce molecules, not ions, so you should see no conduction of electricity. And we see that down below. If we have a strong electrolyte like sodium chloride, then we should be able to strongly light that bulb. If we have a weak electrolyte like the middle case, hydrogen fluoride or hydrofluoric acid, once it's dissolved in water, just a little bit of it goes into the H plus and F minus form. Most of it stays molecular HF, and therefore it's a weak acid and a weak electrolyte. And finally, something like sucrose, table sugar, it dissolves very well in water, but it stays as sucrose molecules rather than a charged species that might give rise to conduction of electricity. So these neutral molecules of sucrose are non-electrolytes because they will not conduct electricity. Okay, so if we want to focus on those strong electrolytes for a little bit, the strong electrolytes are strong because they dissociate or break up completely or nearly completely. Again, that we don't quite tell the truth all the time here in the general chemistry section of the course, but almost 100% break up into positive and negative ions in water. They form aqueous solutions when dissolved in water that will conduct an electrical current. So because the ions are dissolved in water and mobile, they can conduct. If we had something like silver chloride where very little, if any, can dissolve in water, then we wouldn't conduct. So you've got to have the salt, the ionic substance, dissolve into its ions in almost 100% of the cases so that you can have good conduction of electricity by those mobile ionic carriers of charge. And we see just a couple here. Sodium chloride and calcium bromide are both strong electrolytes because they both dissolve completely. So before we get too far into it, let's pause here for a learning check and see how you do with completing those equations for strong electrolytes dissolving in water. So just like on an exam, you've got some multiple choice possibilities for number 1 and number 2 for each of those processes. Go ahead, pause the video here, decide A, B, or C as the correct or best answer, and then start back up and we'll see how you did. Okay, so for that calcium chloride example, the correct answer is C, where the calcium 2+ ions are aqueous, dissolved in water, and 2 chloride ions aqueous for each mole of the CaCl2 solid that dissolves in the water. For number 2, the best answer is A, the potassium phosphate dissolves to give 3 moles of potassium ions aqueous plus 1 mole of phosphate ion aqueous for every mole of potassium phosphate that dissolves in water. So hopefully that was pretty trivial, but again, it's some practice on prior concepts, adding on this idea of strong electrolytes. Now, if we look at the weak electrolytes, these are solutes that don't dissolve completely or really to much of an extent at all. So they dissolve in the water mostly as molecules. A few of them form ions. So you do have a few ions, which is why you get that weak conduction and why that light bulb was struggling. That was an incandescent bulb, so it was able to glow a little bit, but not as bright nearly as the strong electrolyte case. So here we typically have our weak electrolytes, our weak acids and weak bases. So HF there dissolves in the water to form the weak acid hydrofluoric acid. Again, hydrochloric, hydrobromic, hydroiodic, those are all strong acids, but the HF is a weak acid which stays mostly as HF molecules dissolved in water, but only a few, very small extent, 1% or so would be H3O plus and F minus. If we look at ammonia, that's an example of a weak base, and that weak base will dissolve in the water to give mostly neutral ammonia molecules, but again, some ammonium ion and some hydroxide ion. So if you see in the top case, we have a weak acid, so we produce some H3O plus. In the case of a weak base, we produce some OH minus, but in the case of a weak acid or a weak base, mostly we have the molecular species dissolved in water and not too many ions of either type. All right, and the third option that we discussed were the non-electrolytes. So solutes that are non-electrolytes dissolve as molecules in water. So they do not produce ions in water, and they form solutions that do not conduct an electrical current because there's no electrically charged species, at least not enough. The water itself does dissolve a little bit in itself into H3O plus and OH minus, but in a very, very small degree. So here's the sucrose molecule as a solid, and then in water it stays the sucrose molecule, but now it's hydrated. It's surrounded by water molecules, whereas in the solid, it's surrounded by other sucrose molecules in a crystal lattice. So there we go. We can form a solution, at least for a molecular species like sucrose. It's not a weak acid, not a weak base. It's what we call a non-electrolyte. So there we have it. Those are the three possibilities. And again, it's specific electrolytes that the research is done on things like Gatorade and Powerade that suggest they might give you a slight edge, because you could certainly make your own salt water and have electrolytes, but it's not going to be quite the same. All right, and here table 8.4 summarizes these ideas. So we have the different types of solute, strong electrolyte, weak electrolyte, or non-electrolytes, how much they dissociate. Again, completely is a little bit of a lie, but mostly, certainly almost completely. For weak electrolytes, partially, and then non-electrolytes, not at all. The types of particles in a strong electrolyte would be ions only. Weak electrolyte, you've got a mix of mostly neutral molecules and a few charged species. And then finally, with non-electrolytes, you have molecules only. So we already saw in that early slide, the conduction, the electrical conductivity is quite strong in a strong electrolyte, quite weak in a weak electrolyte, and non-existent in a non-electrolyte. And there we have our examples of some common types of solute for each electrolyte class. Here's a term, equivalence. You might see this, especially in the hospital setting. Sometimes you'll see equivalents listed on things like saline bags and that sort of thing. So an equivalent is the amount of that ion equal to 1 mole of positive or negative electrical charge, plus or minus. So if we think about our classic example, sodium chloride, 1 mole of Na plus ions and 1 mole of Cl minus ions are each one equivalent, or 1,000 milliequivalents, because they each contain 1 mole of charge. And if we had ions with charge of 2 plus or 2 minus, then they'd have 2 equivalents for each mole. So 1 mole of Na plus ions would give us 1 equivalent. 1 mole of Ca2 plus ions would give us 2 equivalents. 1 mole of S2 minus would give us 2 equivalents. And again, since we often deal with small amounts of things, you're often likely to see milliequivalents used in the hospital setting. So here table 8.5 shows us some of those examples. Again, the charge on the ion itself, and therefore the number of equivalents in 1 mole of those ions. Okay, so here we see why people are spending millions and millions of dollars every year on those sports drinks. Well, it's because these electrolytes play pretty critical roles in proper functioning of cells and organs in the body. So sodium ions, for instance, regulate water content and carry electrical impulses through the nervous system. Potassium ions are involved in the transmission of electrical impulses and help maintain a regular heartbeat. It's actually potassium chloride that is used to stop the hearts of those people sentenced to die by lethal injection. So again, that's a massive dose of potassium injected directly into the bloodstream, and that causes that effect. Drinking these sports drinks, it's probably not good to drink too many of them, but you certainly shouldn't be able to get that high of a potassium level by drinking those that you would cause any problem with your heartbeats. But again, if you started to feel like something was wrong, then certainly get yourself checked out. And finally, bicarbonate ion helps maintain normal blood pH. Blood pH should be slightly basic, and the bicarbonate ions help maintain that slightly basic blood pH. So if you, like your vinegar on your salad, then you can ingest a weak acid like vinegar without adjusting your blood pH down to where it would be a level in danger of precipitating protein. So all of these electrolytes are important, and they do critical jobs, and therefore we want to make sure that we're making healthy food and drink choices that allow us to have healthy electrolyte balances. And so here we see in table 8.6 some typical concentrations of electrolytes in blood plasma. And as you see, sodium's in quite a larger concentration than most of the other cations, and chloride is the most dominant of the anions. But everything should be there in those amounts, or roughly those amounts, if you want proper functioning of the body. So we don't want to adjust these things necessarily so that everybody's 138 milliequivalents per liter. That wouldn't work well. This seems to work well for optimal functioning of our tissues and organs. All right, so before we leave the chapter, we'll have one last learning check here. So number 1, in 1 mole of Fe3+, there are, and then select from A, B, or C. Number 2, in 2.5 moles of sulfate 2-, there are A, B, or C. And finally, in 3, an intravenous bottle contains only NaCl. If the Na+ ion produces 34 milliequivalents per liter, then the Cl- ion produces A, B, or C. So go ahead, make your selection, pause the video here, and we'll check and see how you did in a moment. All right, in the first example, we have the Fe3+ ion. So because it's 3+ charge, there would be 3 equivalents per mole, right? So choice C was correct. In the second example, 2.5 moles of the sulfate 2-, there would be 5 equivalents. 5.0 choice B, because 2.5 times the 2- charge gives us 5. In number 3, if we have just the Na and the Cl, the Na+ has to be equally balanced by Cl-. They're in a 1-to-1 mole ratio. So if the Na+ ion is producing 34 milliequivalents per liter, then that Cl- ion darn well better produce 34 milliequivalents per liter, choice A. So hopefully this is familiar and comfortable stuff. If that's not the case, certainly reach out and we'll try to help as best I can. But otherwise, if things are going well, as I hope they are, we'll see you again in section 3.